All right, well, Arrhenius theory is not the only theory. There's another theory, which is the Bronsted-Lowry theory. And this one is a little bit more expansive, so it includes some things that might not have been counted as acids or bases according to the Arrhenius theory. So what do we need to know first? You have to remember this, that a hydrogen ion is literally the same exact thing as a proton. So again, a hydrogen ion right here is the same as a proton. So H plus and proton are literally the exact same thing. So a hydrogen ion and H plus is a proton. All right, so here are two of the major theories. We talked about Arrhenius theory in the last video. So Arrhenius acids give away, produce H pluses as their only positive ion in solution, whereas Arrhenius bases give away, have OH negatives as their only negative ion in solution. What about Bronsted-Lowry? What does it change? Well, most of the time you're going to see it defined in terms of protons, but it could also be defined in terms of, ready? H pluses. So Arrhenius is a substance that produces H pluses or H3O pluses as the only positive ion in solution, whereas Arrhenius bases produce OH negatives as the only negative ion. And Bronsted-Lowry, which is what we're going to look at in this video, described a little differently. So as a quick reminder, again, Arrhenius acids produce H pluses or H3O pluses. So remember, they just stick together in solution. Arrhenius bases produce OH negatives as the only negative ion in solution. So let's look at this alternate theory. So we're going to focus on the Bronsted-Lowry theory, which is, for our purposes, usually called one theory or alternate theory. Rarely is it called by its name, so there you go. Remember, a hydrogen ion is an H plus. It is the same exact thing as a proton, okay? So a hydrogen ion is a proton. All right, so let's talk about how that's related to the Bronsted-Lowry theory. Well, we can have donators. Here you go. Take it, take it, take it. No, really, I don't need anything. Take it. Donate. Take it. And we have acceptors. Why, thank you. Why, thank you so much. Why, thank you. We have donators and we have acceptors. Donators and acceptors. Donators and acceptors. So Bronsted-Lowry acid or base. How do you figure out which is which? Well, you follow the H plus. Okay, you follow the proton. Let's see what I mean. So a Bronsted-Lowry acid is an H plus donator or a proton donator. So what do I mean? All right, so let's look. The rule is follow the H plus. So I'm going to look at this equation. I'm going to go, okay. There was some movement of H's, so where did it go? So let's look here. This started as H attached to an F, but on this side, I just have an F with no H attached to it. So where did that H go? Well, it couldn't disappear. So look, this O has two H's on it, but on this side, this O has three H's on it. So the H went like this. It went from here, bloop, over here. So what donated the H plus? Because the acid is the donator. Here you go. No, really, here, take it. So the HF is the acid. The Bronsted-Lowry base is the H plus acceptor. Why, thank you. Or the proton acceptor. Why, thank you. Same equation. The rule is follow the H plus. So again, H attached to F, but on this side, just F. O with two H's, but on this side, O with three H's. So the O moved. Where did it go? This way. So to find the base who accepted, Who accepted the H plus? Well, it was the water, the H2O. So that is the base. Now, just because that would seem so ridiculously easy and we'd be done. There's more. So conjugate pairs. What that means is if it started as an acid on this side and it gave away its H plus, it donated it. Its partner on the other side is called a conjugate base because in the reverse reaction, it's going to accept. So it helps when you look at an equation that has symbols and not just pictures. So let me try. So what is a conjugate base? Well, first of all, it has to be on the product side. So we have an acid base on the reactant side, and then we have the conjugates on the other side. It pairs with a Bronsted-Lowry acid. So we have the acid and its conjugate base, and they're partners. So here's our equation, same one. Follow the H plus. Remember, we followed it here. What donated the H plus? We already said it was this. So the conjugate base is the acid without that H. It gave it away, right? It donated it. So where is it without the H? It's right here. So that is the conjugate base. They're a partner. Acid on this side, conjugate base on this side. So let's look at conjugate acid. Also on the product side. So reactant side, we have acid and base. Product side, we have conjugate acid and conjugate base. This time it pairs with a Bronsted-Lowry base. So here's our same equation. Follow the H plus. Looked at it so many times. The H went this way, right? Who accepted the H? That one, so it is the base. So now look on the product side. What does it look like after it accepted it? Well, that's right here, right? So that is the conjugate acid. Because now when this reaction goes in reverse, this is going to become a donator, all right, and turn into this. So on the reactant side, we have an acid and a base. And on the product side, we have a conjugate acid and a conjugate base. So let's look at it again. So we have a Bronsted-Lowry acid with the conjugate base. And then if we take this base and add an H to it, we get back to the acid. So it could go back and forth, back and forth, back and forth forever and ever. And on this side, it started as a base, so it becomes a conjugate acid on the other side. All right, so let's look at equations. So let's try and figure out which one is going to be the acid and which one is going to be the base. So remember the rule, follow the H plus. Okay. So let's look. We started with 3 H's on this side. Ooh, we only have 2. This started with 2 H's and it has 3. So what happened is an H went like this. So that makes this the acid, the H plus or proton donator. And that makes this the base, the proton or H plus acceptor. So if this is the acid, this is the conjugate base. And if this is the base, this is the conjugate acid. They pair together. Because if I go in reverse from this back to here, I would have to donate, right, to get back there. So that's why it's the conjugate acid. Let's try another one. Ooh, oh gosh. Okay, this one looks complicated. All right, so I have CO3 on this side, and I have CO3, but ooh, with an H. And this is H2O, but on this side, it's only OH. Oh, see, OH, it lost an H, so the H went this way from here to here, and that's how I ended up with that. So if the H plus goes this way, that means this is the acid, the donator. That means this is the base, the acceptor. So that means on the other side, I have a conjugate acid and a conjugate base. Well, which one did this come from? From here. So if this is the acid, on this side, it's the conjugate base, acceptor. And this are paired, so this must be the conjugate acid. Okay? All right, let's try another one. Okay, I have 3 H's. On this side I have 2. Here I have 3 H's. On this side I have 4. All right, so the H went this way, which means this is the donator acid. Oops. Acceptor base. On the flip side, the other side, I need a conjugate acid and a conjugate base. This pairs with this, so that's the conjugate base. This pairs with this, the conjugate acid. All right, let's look at another one. All right, let's check out this equation. Let's find where the H's went. Ready? So I started with 4, I went to 3. I started with 2, I went to 3. So that means the H went this way, right? So that means this is the donator, this is the acceptor. So on the flip side, this must be the conjugate base, and this must be the conjugate acid, right? Hopefully that starts to make sense. But then we throw something else in there. Some things are amphoteric. I just like to think ambidextrous. You know, that means you can write with both hands. Well, amphoteric means a substance that can act as an acid, but it can also act as a base. Water is one of those few substances that's amphoteric. It can act as an acid, donate, and be left as OH negative, and it can act as an acceptor and end up as H3O+. So remember, Bronsted-Lowry acids donate or give away H pluses or protons, and Bronsted-Lowry bases accept H pluses or protons. Okay, so what does water look like when it's an acid? Let's see. Acid is donating. So watch this. The H went this way, left here, went over here. So in this case, water is acting as an acid. This is the base. This would be the conjugate base and conjugate acid. All right. Well, that's not it. Water can also act as a Bronsted-Lowry base. So the H plus goes this way, so it became an acceptor. All right, so it is in fact acting as a base here. On this side, it would be the conjugate acid, and this would be the conjugate base. All right. There you have it. That's Bronsted-Lowry theory. I hope you learned something new today.